last year.
Yes.
Hopefully, she will present his thesis next year. And last work is on transport properties of all electric. Well, it's not the last work, but the last but one, right?
Yes.
So we recently published another paper, but she preferred to present this work on all electric, all-semiconductor spin transistors.
Perfect. Okay, thanks for coming. The title of my talk is The Transport Properties of All Electric and All Semiconductor Spin Transistor. This work has done in collaboration with Joran Serra and David Sanchez, that is my supervisor. The outline of the talk is first, what's a spin transistor? Explain about how operate a spin transistor. The second part is our motivation to study this kind of systems, and then we solve we have an analysis of the one-dimensional case and one more realistic system in which we have transfer modes and we have the quasi-one-dimensional case, and then finally I say a bit conclusions. First of all, what's a spin transistor? A spin transistor operates under the action of a spin-orbit interaction which rotate the spin of the electrons along a narrow channel. Typically, a spin transistor is formed by a semiconductor attached to two ferromagnetic terminals with a spin-orbit interaction in the central region, which we can modulate with this gate. A semiconductor heterostructure gives us the opportunity to generate this kind of spin-orbit interaction due to the inversion asymmetry. And interestingly, the strength of this interaction can be tuned with an external electric field. In this case, we have here this gate to modulate the strength of the spin-orbit interaction in the central region. Although spin precession have been detected in this kind of junctions, in semiconductor ferromagnetic junctions, the spin injecting efficiency tends to be low when we have a junction between these similar materials. A good alternative to solve this problem has been done by the experimental group of Chuang et al., in which they use, I'm sorry, I don't have said that here, the ferromagnetic terminals normally inject and detect spin polarized currents. Then here they use two QPCs to inject and detect the spin polarized currents, and then the electric confinement in these constrictions generate an effective magnetic field that polarize the electrons perpendiculars from to the central region. This fact that the electrons in the QPCs are polarized perpendicular from the central region give us a detector voltage oscillating when we tune the Rashba spin-orbit interaction in the central region. They give us two results in which, in the first one, they have the Rashba fields in the three region parallels, and then they don't observe any kind of oscillation. But when they have the Rashba field in the QPCs perpendicular from the central region, they observe an oscillation when they tune the Rashba strength in the central region. Then we want to study a similar system in which we have two constrictions in the QPCs that define a quantum well in the central region. We also observe that here the Rashba spin-orbit interaction is different from the two QPCs and the quantum well. This is the total Hamiltonian, where in the first part we have a kinetic term and a voltage that give us this kind of constrictions. Here we have two spin-orbit interactions. I start with the second one because the second one is the spin-orbit interaction in the central region. And here the Rashba field is always in the Z direction. In contrast, in the two QPCs, the Rashba field can be tuned from the Z direction to the Y direction only changing the value of this angle phi. This is, for us, the polarization angles. And for example, for phi equal to 0, this term is equal to 0, and then the Rashba field in each region is parallel, but for phi equal to p half, the Rashba term in the Z direction is 0, and here in the QPCs we only have the Y direction, and then the Rashba term is perpendicular. What is crucial in our work is the ability of manipulate the direction of the Rashba field in each region. Then we start speaking about the one-dimensional case. In this case, it's easy to see that our double QPCs is like a double barrier with a quantum well behind the two barriers. Here we also have plotted the energy bands in the reservoirs. We don't have Rashba field, then the states are spin degenerate. But in the QPCs and in the central region we have Rashba spin-orbit interaction, and then the bands are splitting in momentum and also shift down in energies. Then here we have the wave function in each region, when this wave function 2 is the wave function in the central region, and we observe that for S equal to plus, for example, we have an spin-orbit in the direction minus Y always, but in the reservoirs and in the QPCs, the spin-orbit depends on the angle alpha. We also observe here that we don't have fixed the spin quantization axis in the reservoirs. We have the spin quantization axis of the reservoirs always parallel to the QPCs. Here we have the momentum in each region where L indicate the direction of the motion of the momentum, and S is the index of spin. Then we now can solve the scattering problem, and we have to, using the matching method, we obtain the matching conditions. This first one is the typical in which the wave function have to be continuous in each interface, but the second one comes from the flux conservation. If we don't have Rashba spin-orbit interaction in any part of the system, we recover the continuity of the function derivative. Then we can study the probability reflection and transmission, in this case when we tune the angle phi. We remember that for phi equal to 0 means that the Rashba field polarized the electrons parallels along the system, and phi equal to 1/2, phi will be 1/2, the electrons are polarized perpendicular. Then in the first one, we have all the parameters difference to 0, and observe that, for example, the electrons always are reflected in the same spin-orbit that are incident. This is because we have the polarization axis in the reservoirs parallel to the polarization axis in the QPCs. Then all the electrons are reflected in the same spin-orbit. But in the probability transmission, we observe that we have both contributions. Only for phi equal to 0, the off-diagonal transmission is equal to 0. This is because in the parallel configuration, we don't have a spin polarization. Now, in order to understand better why we observe this, we studied 3 different cases. In the first case, we have removed the QPCs. We have L1 equal to 0. Then we observe that our system is completely transparent. All the electrons are transmitted, and we observe that the behavior of the transmission is similar to the first one. This indicates that the QPCs don't give information about this kind of motion, of modeling of the transmission. Then we we take only alpha 1 equal to 0. We only remove the Rashba field in the QPCs and observe that the behavior is the same as in the first plot, but the transmission is lower. This gives us information about that the Rashba field in the QPCs increase the probability transmission. This is because this, the effective effect of alpha 1 is decrease the top of the barriers. And finally, if we only remove the Rashba field in the center region, we observe that the different probability transmission and reflection are independent of the polarization angle. This said us that all this behavior is due to the Rashba field in the center region. Then, what we observe is that in the parallel case, our system is more simple, because in this case, the Rashba field polarized the electrons parallel in all the system, and then if we project the Schrödinger equation on a spin channel along the direction minus y, we obtain this equation. That if we apply an appropriate gauge transformation, we can write in this other simple form, where V1 is the height of the tunnel barriers. And here we can see better that the role of the Rashba spin-orbit interaction in the QPCs is to lower the top of the barriers. And V2 is proportional to the Rashba field in the center region. Then V2 is the depth of the quantum well in between the tunnel barriers. If we solve this scattering problem, we can obtain the resonant condition, which depends on all the parameters of the system, where this K2 is the momentum in the central region, L is the length of the central region, and this F is a complicated form that depends on alpha 1, alpha 2, and L1. Then we have the ingredients to understand better this plot. In this plot, we have the probability transmission diagonal and diagonal when we tune, when we tune the Rashba strength in the central region. In the first case is the parallel case, in which in this plot we have tunnel barriers, but in this other we don't have tunnel barriers. We observe here that at certain values of alpha 2, the probability transmission has peak resonances. This is because as deeper is the quantum well, new quasi-bound states appear into the quantum well, and then when these states are resonant with the incident Fermi energy, we have a maximum in the transmission. These peaks obey this resonant condition from here. We also observe that here all the electrons are, Then this is an analog of the Fabry-Perot resonator that is tuned with the Rashba spin-orbit interaction. Then we observe that all the electrons are transmitted in the same spin that we incite. We can explain better this if we remove the QPCs, then we remove the Fabry-Perot resonances, and then we only observe what happened with the Rashba field in the central region. We observe here that the system is completely transparent, and only for high enough values of alpha 2, we observe these wake oscillations that are due to the Ransauer effect. Here, the system is completely transparent because at this energy, the electrons don't feel the well discontinuity, and only for higher enough values of alpha 2 starts to feel a bit this quantum well. Then what we then now we increase this angle, and then the electrons in this case are polarized 45 degrees with respect the axis minus y. And then for L1 equal to 0 without QPCs, we start to observe that the probability transmission is modulated. This is due to the data dash effect, and observe that for alpha 2 equal to 0, the off-diagonal transmission is equal to 0, and the other one is equal to 1. And as we increase alpha 2, these two transmissions are modulated, and this is because for alpha 2 differing to 0, the band's energy is split in momentum. Then we have to see that this oscillation, the origin of these oscillations is completely different from the origin of these resonances. These resonances. These oscillations are due to the data dash effect, in which the probability transmission, when we don't have QPCs, is proportional to the cosine square of delta k L, where delta k is the splitting of the bands in momentum, and L is the length of the central region. Then the maximum condition is different. Now, if we turn on the tunnel barriers, we observe the combination of both resonances. And here we have a superposition of the Fabry-Perot resonances and the data dash oscillation. If we increase the angle between the Rashba field in the QPCs and in the central region, we observe that for L1 equal to 0, the data dash oscillation goes from 0 to 1. And when we have the superposition of both effects, we have this kind of plot. Then now it's natural to ask what's happened now if we change the length of the central region. First of all, for the parallel case without QPCs, our system is completely transparent. This is in agree with the previous result. But when we have the tunnel barriers, we observe resonances that are X-spaced. These resonances are due to, if we increase the length of the central region, new internal modes appear, and then when the Fermi energy, the incident Fermi energy is in resonance with one of these new modes, the probability transmission is maxima. This is maxima. Well, this is also another property of the Fabry-Perot resonances. Now, if we increase the angle between the polarization angles, we can start to see the spin precession effect, where this frequency is different, from this other, okay? Confronts the same maximum condition, but the behavior is the same, but the frequency is different. And we observe that that's oscillation, and when we turn on the tunnel barriers, we have a superposition of both. What we have to see here is that when we have the superposition of both oscillation, the probability transmission becomes quasiperiodic. The quasiperiodicity is one effect that we need at least two oscillations whose characteristic frequency is uncommensurable, and the ratio between the two frequencies gives us an irrational number. In our case, the Fabry-Perot frequency takes this form, and the spin precession frequency takes this other form. And quite generally, the ratio between both is an irrational number. What is important here is that this effect, the origin of this effect is totally quantum. Then we have explained it a bit, the one-dimensional case which, oh, sorry, I don't have said before, the one-dimensional case is a good approximation when we work with evanescent states in the QPCs. All the time we have evanescent states in the QPC, but now we want to extend our analysis to a more realistic system, and then we consider the quasi-one-dimensional case. Here we have two QPCs embedded into a quantum wire with a finite width. Then we have to take into account transverse channels that are coupled via the Rashba intersubband mixing potential. Then here we have the two QPCs. What we have here is in our numerical simulation, we have a hard wall potential in the y direction and two square QPCs in the x direction. We also have a strong confinement in the growth direction because only the lowest subband can be populated. Then our wave function is a combination of spin channels and spin agent states. And if we project the Schrödinger equation, this and this other. And if we project the Schrödinger equation on a given spin channel, we obtain the spin channel coupled equation, where we observe that VA and VB are that due to VA and the VB, the states with different channels can be coupled. Here, VA and VB are these two formulas in which VA contains the Z component of the Rashba field in each region. This is the Z component of the Rashba field in the first QPC, in the center region, and in the second QPC. This is only the Z component of the Rashba direction. This component is only different to 0 when phi is different to p half. This VB contains the y direction of the Rashba component, and we only have y direction in the first and in the second QPC. Now, if we take now our agent state in the minus y direction, we obtain that this term is diagonal, but this other one, no. Then we have a coupling between different spins due to VB and due to VA. If VB or VA are different to 0, we have coupled channels. Then we can make this plot in which we also show the probability transmission when we change alpha 2, but now for our quasi-one-dimensional case. What we observe that for the parallel configuration, the peak resonances are qualitatively agree with the quasi-one-dimensional case. And we also observe the Ransauer oscillation when we don't have QPCs for lower values of alpha 2. This is okay because the Rashba intersubband coupling is negligible for small values of alpha 2. But what happens when we increase alpha 2? When we increase alpha 2, the mixing term starts to play a role, and then, for example, for L1 equal to 0, we obtain these dips, and when we have the two QPCs appear new resonances. This is because, for example, when alpha 1 and alpha 2 is equal to 0, we don't have a spin-orbit interaction in our system. The cavity works as a resonator with multiple resonances. Then, if the cavity is closed, the bound levels can be described with a pair of natural numbers n1 and n2. Is a good approximation. Then is a good approximation that when the cavity is open, the electrostatic scattering obeys a conservation law that fits the transversal momentum. Then N2 have to be conserved along the system, and the transmission shows less peaks than bound states in the closed cavity. But now in our system we have alpha 1 and alpha 2 different to 0. Then the conservation law don't have to hold, and then more resonances emerge. Then now we increase the polarization angle and appear the spin precession effect. And also we can see that only for small values of alpha 2, we can compare this oscillation with the quasi one-dimensional case, this and this one. But when we increase bigger, when we have bigger values of alpha 2, for example, the data dash oscillation is not given by a finite frequency. And when we combine both effects, we obtain that the probability transmission gives us more resonances that is not possible understand this with the quasiperiodicity. If we increase the Rashba field, we have the same behavior for small values of alpha 2 and a chaotic behavior when we have alpha 2 bigger than, in this case, 30 millielectron volts nanometer. Now we want to understand a bit more this system, and now we want to tune the value of the length of the center region. But now we want a value of alpha 2 in the range in which the system, the mixing term has more importance. Then here we have alpha 2 around the 55 millielectron volts nanometer. And if we want first to see the data dash effect, we need to take the L1 equal to 0. We want to remove the Fabry-Perot effect. And in this case, for the perpendicular case, we obtain this kind of resonances that are due to the data dash oscillation. But if we compare this with the one-dimensional case, we observe that this is very different. This is due to the mixing term play a very important role here and destroy the oscillation. If we want only see the Fabry-Perot resonances, what we have to take is the parallel gate with QPCs, and then we observe these resonances. We observe also that this behavior is not chaotic as the first one. This indicates us that the mixing term is more important for the data dash effect than from the Fabry-Perot effect. Because if we compare this with the one-dimensional case, we observe also more resonances, but more or less is very similar. Now, if we combine both effects, we obtain this kind of picture in which the quasiperiodicity doesn't exist. And here we can compare, and we observe that it's very different. Then, to finally, we want to extend our analysis when we tune the Fermi energy. In the first case, also we want to see the data dash, the spin precession effect, and we take L1 equal to 0 and observe that the total transmission is approximately quantized when a new channel is open. These are the energies when in the reservoirs or in the QPC a new channel is open. From 0 to 1.23, any channel in the reservoirs is open, then is open the first one, the second one, and from here the third one. But in the QPCs, the first channel is open for energies around the 5 millielectron volts. Then, if we want to observe only the Fabry-Perot resonances, we observe that from 1 until 5, these peak resonances are only due to tunnel transport between the QPCs, because any channel is open in the QPCs, but one channel is open in the reservoirs and the quantum well. From 5 to 11, we have one channel open in the QPCs and one channel open in the QPCs, and the second channel is open in the reservoirs. And then we also observe the transmission that goes only until 1. This is because two channels are open in the reservoirs, but only one in the QPCs. For energies bigger than the third channel, we start to observe these dips and peaks in the diagonal and off-diagonal probability transmission. Then, if we combine both effects, we obtain this chaotic system. And then, finally, in conclusion, in the one-dimensional case, the probability transmission show Fabry-Perot and data dash effect that both oscillations, when both oscillations are together, we can explain the probability transmission with the height of the quasi-periodicity modes. And then when we have the quasi-one-dimensional case, in which we take into account the transverse models, the Fabry-Perot and data dash oscillations breaks at certain values of alpha 2, and also the Fabry-Perot, and also the quasi-periodicity disappear. And thanks for your attention.
Thank you, Rashba. Questions?
So why you call superposition of the two effects? I mean, there is
Yes.
something that tells you that indeed they are superposed one oscillation to the others, or is
Ye-
there a way to say that you have both effects?
I have both effects simultaneously, and then I say superposition because it's in the first plot that we see. In the one-dimensional case, it's easier to see. Here. Okay. I say superposition because if you superpose these resonances on this other effect of the data dash oscillation, we can see how this over this is the red one, and over this other is only the blue one. I say superposition because visually it's a superposition of both oscillations. This is the reason because I say superposition and not the two effects together. How we define the?
You have two parameters. Okay, I understand when you have alpha z in that direction, and in y direction, how do you define? If it's critical.
Yes, in the first experiment, it's better maybe. In this experiment, they do this. In this experiment, they I don't know where it is. In this experiment, they do this. In the QPCs with an electromagnetic confinement, they can change the orientation of the Rashba field.
No, this I understand, but in usual experiment, I mean, like question about alpha 1 or alpha 2 in principle, it's quite, how to say, it's one of the questions how to define strengths of Rashba interaction. Sometimes they say material, one gallium arsenide or whatever, they have some idea. They don't know exactly.
I don't know exactly how.
Right, and so you use it on the adjusting something, or how was alpha 2 parameter was chosen?
How I choose?
When you
Because in this experiment they use these values of alpha 1 and alpha 2. Yes, they use these. Yes. Yes.
There's some measurements that Isabel can show. They also detect electrically these oscillations of function magnetic field. And from
yes, then I understand.
the dependence with the magnetic field, they are able to extract the value from here.
No, no,
You
don't.
can do magnetic field. What I'm saying is that using the magnetic field, you can estimate
Yes,
strength
yes,
of
I
the
know.
transfer.
And I mean, because it was in the beginning my question, all electric all semiconductors is for any semiconductor or
No, no. Semiconductor only means that all the system is a semiconductor. We don't have different materials. This is only the meaning of all semiconductor.
As compared with the previous, can you maybe go back? Here, the ferromagnetic sites are layouts.
Hmm.
Why is it so ferromagnetic is here?
Okay.
Would you conclude then that the Fabry-Perot resonances are good for the spin transistor, or they are useful or helpful? I understand you have this data dash oscillation, which are the standard oscillation of the spin transistor, and you discuss these other.
Yes, the Fabry-Perot.
They are helpful or useful, or something that one has to.
I don't
Have a
know.
calculation of
Yes,
of the resonances.
yes. Have when normally when you sum the two components, we always recover the Fabry-Perot. The data dash oscillation, the data dash effect only is visible when you can measure the probability transmission diagonal and off diagonal separately. If you can't measure it separately, you only can measure the total transmission. Only the Fabry-Perot resonances are visible.
But let me make also a related question, because usually when we speak about spin transistor, we would like to use a certain polarized current, right?
Hmm.
And you show that when you don't have, for example, point contact, then it seems you have polarized current, right? You have very nice one, but as soon as you have this point contact, you immediately destroy this property, because you don't know, you have very large oscillation, and you don't know really which spin you carry by this current. You understand?
No.
I mean, spin transistor is, I mean, idea of spin transistor that you can control by, for example, strength of electric field, the degree of mixing of current of spin. You will then, for example, use spin up or spin down, for example. This is how spin transistor.
Yes.
But then you show that if you have point contact absent, then you have a nice polarized current, as far as I understand.
When you remove the QPCs, we don't have a spin transistor because we only have a cavity with a Rashba spin orbit in the central region. Yes, this is in the parallel configuration, because I think that I say that in the parallel configuration, for example here, we don't have a polarized current, because you inside with positive electron and you only recover positive electrons, and then the system is completely transparent. Here I don't have polarized anything.
But it's transparent for K++, spin up.
Yes, I only inside for with electron with positive spin, and then we don't have any electron transmitted with opposite spin.
Yes, exactly.
Yes.
Then it means you
Transparent.
spin transistor. You transfer only spin up.
But if I only inside with a spin up, if the system is transparent, it's not
spin
polar.
up, and
Yes.
also spin down. Yes. K++,
Yes.
1.
Plus
Plus
0.
0.
Yes.
It means you open system only to spin up.
Yes. Yes. Yes.
This is
Yes.
aim of experiment. And then when you have, I mean, it's how I understand result. And then if you have point contact, then you mix everything.
I only lose this property when the probability transmission have a minimum. That is because we don't have, in this case, for example, we don't have the intrinsic modes. We don't have these modes in resonance with the incident energy. This is destroyed only because here our system is an analog. ¿Entiendes?
We need some modulation of the current.
Yes, yes, my
So
question
in the first figure, the cycle is flat.
yes.
Okay, so you can tune it.
Yes.
Okay, so all parts spin out and closer go through, and that's all. But, however, when phi is equal to pi over 4 or phi equal to pi over 2, then you are really seeing these data as oscillations. So what you really want is to tune these and to go from up to down, to
Yes.
really cause a precession, spin precession.
Yes, yes. But without point contact.
Yes.
Because L1 is equal to 0, is satisfies and understood.
Exactly, yes.
But as soon as you have a point contact, you lose all this property. Because that figure shows that you completely have a mess. Because here I see L1 equal 0, I see up one red curve is 1 and blue 0. Then a particular this
But this is because the incoming spins are polarized, taking in the
yes,
calculation, taking the spin.
so my question is very simple. So point contact destroys the spin the transistor.
I'm not calling this destruction,
No.
it's just that it induces a modulation of the
Yes.
It induces spin fields.
Yes.
Or spin precession.
Okay.
Okay, maybe that is better. Okay, so if